Okay, so good afternoon, everyone. We think everyone who was in the waiting room has now been let in. So welcome. It's good to see some familiar names as part of this who've been attending this series of seminars put together by the TAPAS network. I'm Paul Linden, and I'm going to chair this seminar this afternoon. Just a couple of housekeeping announcements. One is that we will be recording this presentation as usual. So if you do not wish to be recorded, please turn your camera off and don't stay on mute. In any case, please stay on mute during the presentation so that we're not interrupted by background noise. As usual, please put your questions for Doug in the chat, and we will go through them in the discussion period at the end of this presentation. So it's a pleasure for me to introduce the speaker this afternoon, Douglas Booker, who's the CEO at the National Air Quality Testing Service. He's the co-founder, and they, NAQTS, provide holistic indoor air quality information using high quality air pollution monitoring technology. Doug is also a part-time PhD researcher at Lancaster University, so he's obviously a very busy person, so we're very pleased to be able to snatch him away from these dual roles for the purpose of this presentation. So without further ado, I'll just hand over to him to take us through his talk this afternoon. So thank you, Doug.
Thanks for the intro, Paul, and thanks everybody for coming along. Looking forward to presenting today on what is pretty topical, being with schools reopening this past week, on indoor air quality in schools around the UK. We measured quite a few different pollutants. There's been a lot of talk at the moment recently around CO2, but we're going to be digging a little bit deeper and thinking a bit more holistically. So just as a bit of context about who we are at NAQTS and what we do, we recently celebrated our 6th birthday this week. We were founded in 2015 to raise awareness of indoor air quality. It's a family business, and we comprise engineers, both mechanical and electrical, and we wanted to raise this awareness through developing tools and technologies that could provide the sort of information we need to make informed choices. So we principally operate in two main areas. We design, develop and manufacture our own equipment. This picture you see at the top and over my right shoulder is our V2000 device, which is what was used in the school study here. But we also then use these equipment and other air quality monitors to provide testing services. And that is anything from understanding compliance with environmental certification schemes, helping building operators optimize their buildings for healthy indoor air quality and energy efficiency, but also to evaluate interventions in the built environment. So what I'm going to talk about today is some of the work that we have done measuring in schools. This presentation will include some of the data from around England and Wales from 20 primary schools. This was in year 6 classrooms. And as best as possible, we tried to replicate in our sample something that would comprise a range of different testing locations from, as you can see on this map, quite a few in London and suburban London, but also other parts of the UK, as well as more rural testing locations. And as I mentioned, we're really interested in this holistic understanding of indoor air quality. So we wanted to take as many measurements as we possibly could. All of the measurements that were done throughout this project were facilitated by our V2000, and that consists of both real-time measurements taken at 1-minute intervals continuously throughout the project, but also some discrete air sampling using desorption tubes, which can be facilitated through the V2000 to get a bit of a deeper dive look at speciated VOCs, as well as nitrogen dioxide. So these are the main pollutants that we measured. It was PM2.5, ultrafine particles, so PM.1 and below, nitrogen dioxide, volatile organics, so speciated and total, as well as carbon dioxide, CO2. Now, all of this data was automatically beamed to an NAQTS cloud so that the schools could access their data for a couple of reasons. One, so they could investigate it in near real time, but also so they could use it to inform some of their STEM activities in science classes. And the sort of activities that were underway were quite simple things about looking at trends of different air pollutants to try and see which pollutants are at greater concentrations when they're less, and which pollutants might correlate with each other and what that might mean for potential sources. So this project was really quite big data led. It collected more than 2 million rows of data. So it was critically important that we had the back end infrastructure to manage all of this information. Now, in the title for this talk, I mentioned that measurements were taken pre and post COVID. This, of course, wasn't our original plan. The project actually had to be cut short due to the first COVID lockdown, but we did decide to supplement these measurements by doing more monitoring during the autumn. And I use this graphic on the right to illustrate this through the CO2, through the spring monitoring campaign we did, where green is lower, red is higher. In the top left here, you can see the key. So for those of you who are familiar with the sort of concentrations we might see indoors, you'll probably gasp at how high it could get. But this portion on the right here quite clearly demonstrates when COVID lockdown began, simply because it was a much, this shade of green meant non-occupancy. For those of you who are thinking about what these data gaps might mean, one of the very important things when you're doing measurements in schools is to try and be as inobtrusive as possible, because kids quite rightly are thinking, well, what is this device humming away in the background? So this was the case of pesky children deciding to see what would happen if they turned the monitors off. So for those of you involved in measurements in schools, that is always a key tip of mine, that make sure you get the kids involved in the measurements so that they're invested in the results. Now, I mentioned that this was a two-prong sampling campaign, and that gave us some headaches, of course, because the monitoring that we had done in the spring and then later in the autumn, it was under very different conditions. Now, for those who are involved in indoor air quality measurements, we know that seasonality plays a very big role in the way that indoor air quality can be represented and the way buildings are operated. But this really was even greater so based on some of the engineering-based advice that had come around to manage potential airborne virus transmission. So beyond seasonal effects such as wind speed, minimum temperatures and sunshine, actually the differences in ventilation that we saw in terms of air change rate between the two sampling campaigns was quite staggering. So during this presentation, we're going to try and make these comparisons by focusing on trends and then new insights that came from this autumn monitoring campaign. Now, to begin with, CO2, this is very much an in vogue measurement. We featured on a BBC report last week with David Shookman, because with schools going back, there's huge interest in measuring CO2s in classroom as a form of proxy for ventilation rates. This is being more widespread. This is where the Department of Education sets guidelines around certain concentrations. And this is done for a few reasons. Of course, CO2 is primarily coming from, from exhaled breath. And in times of COVID, where exhaled breath might carry infectious viral particles, we know that high concentrations are likely to lead to greater chance of infecting somebody. The sort of concentrations we see in classrooms are not typically going to be toxic. However, there is literature out there suggesting that concentrations greater than 1,000 ppm may affect things like cognitive function. Anecdotally, we can probably remember from our school days those periods in afternoon classes where we may have had something like double maths where our concentration wasn't so great. And, you know, anecdotally, it would make sense for us that this could be attributed to CO2. I've included here a couple of time series just to illustrate what a typical daily and weekly CO2 profile in these schools might look like. This daily CO2 shows the background CO2 here in blue, around 500 ppm. The start of the school day sees a significant increase up to around 2,500. We then have our morning break, a small decrease, the second period, lunch break, the final period before the end of the day where we see this long exponential decay. As you can see, the concentrations in this school were getting quite high. We saw this in many of the schools where we monitored. In some cases, it would exceed 5,000 ppm, so more than 10 times background, where we start to get into these sort of impacts that are really going to affect children's learning outcomes. And of course, if we look at this across a week, we see very similar patterns just across the different school days. So this is something that is quite repeatable. But it is this ability of CO2 to be used as a function of room occupancy and ventilation rate is where it becomes particularly valuable. As a snapshot for what some of this CO2 data looked like in the spring campaign, where we have here in blue, lower concentrations, red higher. You can see the sort of ranges of concentrations we were getting. We made all of these measurements under real world use, which meant we had no visibility on when windows and doors were open. We know that this is going to have an effect on the CO2 concentrations in the classroom, but unfortunately that is one of the things of doing research in the real world. And we could see a clear impact of the presence of children. If we pick a school, we can see the different school days where there are much higher concentrations. We can see half-term periods, and likewise we can see when the lockdown began. But I think the key message for CO2 is that we really do see a lot of variability between the different schools. And what I'm showing you on this slide here are the air change rates, both during in this case, the spring measurement campaign with the associated histogram, but then also some of the differences between the two monitoring periods. For those of you who aren't familiar with the terminology of air change rate, it's the measure of air volume added to or removed from a space in 1 hour. And I think a very key point to make here is that we would consider it as air entering, not air leaving, because an air change rate of 1 per hour doesn't mean that all of the air in one room is recycled. We must remember that there'll be certain dead points within a room where air can stagnate, which means it can take longer than 1 hour for that air to exit. So returning to this mean air changes per hour and looking across the school, we can see there's a lot of variability, but really what is quite staggering is that we are seeing quite a few schools at the lower end of the mean air changes per hour that we would like to see. A lot of guidance around COVID has been moving towards suggesting best case of up to 6 air changes, and we could clearly see in our spring measurement campaigns that most schools are under 1 air change per hour, so we know this is very low. And if we then put this in context of comparing it against the autumn campaign, well, we did see, which is the good news, significant increases in the ventilation rates. Now that might come down to seasonality, but from the conversations we were having with the schools, it was also some of the engineering-based advice they were getting on if they were naturally ventilated, perhaps opening more windows, or if mechanically setting demand-controlled ventilation set points a bit lower, perhaps to even 400 ppm to really ramp it up. And of course, this difference in air change rate corresponds to lower average CO2 concentrations in the classroom. During the spring campaign, a mean of around 1,500, so we know this is far too high, and I'll touch on that in a moment. And during this autumn campaign, closer to 1,000, which we might consider still to be a little bit too high. Now, if we relate these concentrations to the sort of guidelines that schools are getting, they go by the guidelines from the Department of Education, that's BB 101, which sets these guidelines, which you'll see in the bottom left here, and they separate these out by both natural and mechanical ventilation, and they set two guidelines, one for daily average concentration during occupied periods, and the other about maximum concentration thresholds. And this top image here shows the mean concentrations of CO2 across the schools over both periods, blue in spring, pink in autumn. And we can see in most cases, even though there were a mixture of natural and mechanically ventilated schools, for a simple comparison here, we went with the higher, which is natural ventilation. Most were above the recommended guideline for daily average CO2. As I said previously, we did see an improvement in the autumn, but for those of you who look at total, average concentrations, we're still probably a bit too high. And then relating this to the compliance against peak standards, these correlated quite well. So if you were failing one of these standards, whether that was mean or peak threshold, you are likely to be failing the other. We did see that peak standards were more likely to be breached due to sharp changes in concentrations. And I would say overall, the CO2 concentrations were generally much higher than would be ideal in schools. Now, looking at the key parameters that were influencing CO2, what was particularly interesting is that this shifted between the two monitoring periods. In spring, it was much more about the ventilation rates, temperature, and room occupancy key factors. So looking at our analysis here, we would see that an increase in ventilation lead to a decrease in indoor CO2, likewise with ambient temperature, whereas it's a positive relationship between child density and indoor CO2. More children, more exhalation, greater indoor CO2, makes sense. However, for the autumn, we would no longer see this clear relationship between ventilation, in this case expressed as air change rates, and mean CO2. Because we were having much greater ventilation rates, it actually became child density that was the most significant impact on indoor CO2. Now, this has been presented on in previous TAPAS seminars. CO2 has been a really popular measurement to make over the past year to try and link it to the potential for airborne virus transmission. So this takes us a step beyond just well-being in terms of cognitive function, because CO2 has been used as a very good probe for this infectious risk of airborne viruses. So in this case, we applied some of the data we collected from the spring measurement campaign to look at both the probability of infection for given diseases and the indoor air rebreathed fraction. For those who aren't familiar with this phrase, what I'm about to say isn't going to be particularly pleasing, but it is essentially the percentage of indoor air that you are breathing that is the exhaled breath of somebody else. Of course, again, in times of COVID, that's significantly important if that exhaled breath has any viral particles in it. Now, we've presented this data previously, and I know that Professor Paul Linden, perhaps he can talk about it in the Q&A afterwards. They've just published a new paper on this sort of work, whereby increases, in this case, this is the ventilation expressed as a volumetric flow rate of air in cubic meters per hour, and a probability of infection for various diseases, 1, 100%, 0, 0%. And if we were to look at SARS-CoV-2, increases in ventilation, even subtle increases of, say, 100 cubic meters per hour, can have drastic improvements in the probability of infection. So in this case, around a 60% improvement. And as we follow this curve down, as we get to 200, it might move down to 0.3 probability, so a 70% improvement. However, the point we would make here is because of the shape of this curve, there is a significant diminishing return. So perhaps the engineering-based advice we had during the first lockdown, perhaps even the second, to maximize ventilation at all costs, isn't going to be the best strategy if we think about indoor air quality, and we mustn't forget energy efficiency. Now, moving beyond CO2, having a look at particulates, we measured ultrafines and PM2.5, and this is going to be a real whistle-stop tour of some of the measurements we did, but I urge you to get in touch if you'd like a longer conversation around the aerosol work we did. Again, the key point is that we saw a very diverse picture between the schools and over time. And this really links to one of the key problems with ultrafine measurements is what is an acceptable concentration. They're not measured routinely in ambient air quality anywhere. There are a few super sites in the UK that are making these measurements, and there is no threshold that is universally agreed upon for a safe level. In this case, we set a higher limit here, this HL, at around 10,000 particles per cubic centimetre. Of course, the number of particles that you measure depends on the measurement device you're using and how small a particle it can count. But nonetheless, we chose 10,000 in this case. What we did see is that there was no real correlation with PM2.5 concentrations. That's probably expected given the different sources and different transport mechanisms. We also didn't see a significant impact of the school location between rural, suburban and urban. But what was significant was the presence of a kitchen within the same building where we took the indoor air quality measurement. So from that, we really deduce that the main source of ultrafines were likely to be internal to the school. We did also see some evidence of secondary organic aerosol associated with cleaning activities again, but this wasn't particularly significant and isolated to only a few of the schools where we measured. Moving on to the PM2.5, which is more comfortable terrain for many people because it is regulated in air quality legislation in the UK. In this case, we've taken the annual mean concentration guideline from the WHO of around 10 to look at our data. Again, it's a very diverse picture. And what you will probably notice from the sort of concentrations we're seeing here is that almost all of the schools are meeting the PM2.5 WHO guidelines, although it is worth mentioning they did all exceed the recommended levels many times during the monitoring campaigns. Likewise, on this graph here, we do show both of the different monitoring periods, but there wasn't any significant difference between the two monitoring periods for us. As would probably be expected, we saw a very strong impact of the weather on the concentrations. So looking here at our analysis, where we saw strong correlations between outdoor PM2.5 and indoor PM2.5, and all of the sorts of parameters that we would expect to see to have positive or negative correlations with PM2.5 were at play. Now, as an illustration for these sort of correlations, one thing we noticed during our monitoring campaign is that there were quite a few nationwide episodes of high outdoor PM2.5, and we did see strong correlations in these outdoor episodes and then what we would see in the classroom. And if we look at these box plots here, you can do a Chi by eye to really see that sort of correlation, although we do have some more advanced statistics on that. And I think what is particularly interesting here is that it's further evidence for something we already knew, that air pollution doesn't bounce off the front door, it doesn't bounce off the classroom window. What is outdoor is coming in, what is indoor is going out. And that sort of further complicates some of the story we have around how we can improve indoor air quality. Now for NO2, the sort of sensing technology we use, I'll always use this disclaimer, and I'll say this as a company that use them and develop them. In this case, for those who are interested, we used a combination of both electrochemical and metal oxide nitrogen dioxide sensors, but we also used diffusion tubes to try and get a better time-weighted average across some monitoring periods. These sensors are very powerful for greater spatial resolution, good temporal resolution, but of course I would always take the absolute numbers that come from these sensors with a pinch of salt. Looking at the differences here then between the spring and autumn concentrations, we do see that in some cases the indoor NO2 concentrations is higher than this annual mean concentration guideline. But I think what is more important is that, and I use this as a guide, we do see clear daily NO2 concentration cycles associated with activities, whether that be traffic or something else. And we can see this on this, this time series above with blue out of school hours, pink in school hours. And we can clearly see periods with less activity outdoors, having lower concentrations indoors here. So as with PM 2.5, we did see a strong correlation between some meteorological and weather variables. However, the relationship between indoor and outdoor wasn't as concrete as it was for PM 2.5 for us. Now, I'm whistling through this because I'm really keen to have time for as many questions as possible. One of the things that we did do on this presentation, on this report also, is get quite a extensive look at the volatile organic compounds that were present in schools. And these are coming, as we know, from a variety of different sources. As with anybody who's done this sort of work before, when you do GCMS analysis of these thermal desorption VOCs, you get an overwhelming number of different compounds that are present, some which perhaps you cannot pronounce, some which you've never seen before. But across some of the sampling we did, we really did notice that of the 80 main VOCs we identified, there were 5 that were overwhelmingly present. They were limonene, which is very common in cleaning products, the aldehydes, so acetaldehyde and formaldehyde, largely from some of the cosmetics and furniture and furnishings, D5 from cosmetics, and I think what is particularly interesting is we saw quite a bit of ethanol, which is coming from some of the cleaning products we use, and disinfectants. So we wanted to do this full speciation to sort of go that little bit further than just looking at total volatile organics, which is, which we show here is mandated in the guidelines from the Part F building regs. Because quite frankly, TVOC is something which might be a helpful proxy, but really doesn't mean anything without knowing what the volatile organics that make up that total signal were. So we did see that in most cases, these schools were below the sort of concentrations that you would want to see, which is good news. They were below the Part F recommendations of 300 micrograms per cubic meter, although there was only one school that was significantly above. Now, if we dig a little bit deeper and start looking at what these different compounds were, of course, for those of you who are more eagle-eyed, we'd always be concerned when we start seeing higher concentrations of these nastier VOCs, such as formaldehyde and acetaldehyde. It's worth mentioning at this case, the concentrations were below the recommended annual mean concentrations, and these were likely to be explained by recent refurbishments. But this is the sort of ongoing work that we're doing, we think is pretty interesting for providing this holistic understanding of school indoor air quality. And you may have seen my lights just dim. I'm in an energy efficient lighting office. So they do like to shut off halfway through longer presentations, but we are based in Lancaster University Environment Centre, so it's probably good that they do have those lights. Now, thinking about the key parameters that were influencing these VOCs, it's all the typical things we would expect to see: room occupancy, temperature and ventilation, very significant for influencing TVOC concentrations. Greater ventilation rates lead to a lower indoor VOCs, higher ambient temperatures and child density, greater VOC concentrations, what we would typically expect to see. I think what was particularly interesting is that the parameters were more significant during the spring campaign when the ventilation rate was lower. But what I found particularly fascinating through looking through some of this sampling is the sort of equilibrium effects we saw between the use of certain cleaning products in these school classrooms and these greater ventilation rates. So I've just picked a few schools here to illustrate a point of a few of the different sort of VOCs that are used and associated with either disinfectants and or cleaning products. And we, between the different monitoring campaigns of the main, which is the spring, and the extension, which is the autumn, we saw some pretty significant increases of cleaning related VOCs which when we then relate it to the increases in ventilations between the two campaigns, meant that actually we were seeing pretty much, although not particularly statistically significant, greater VOC concentrations in the autumn campaign than we did in the spring, which means that it's probably what we expected. And for those of you who are slightly critical of the overwhelming focus on fomite transmission, would see as us over sanitizing some of these spaces. So really looking forward to your questions here. A few sort of points to finish on. I think the key message here is that school indoor air quality is really quite diverse across space and time, and that's for many different reasons. There are a lot of different factors, including indoor and outdoor sources, how the building is made up, what materials are put inside, when it's been furnished, how the building is being used, outdoor air quality concentrations, etc., etc. I think some of the good news we saw that is marks the difference between our spring and autumn measurement campaign is that there were significant increases to the ventilation and subsequent reductions to in-classroom CO2 concentrations. However, we would, as a company that are interested in holistic monitoring, slightly push back on the use of CO2 as a overall proxy for indoor air quality. Now, as a disclaimer around what I'm saying, I'm not saying that schools shouldn't be investing in these portable CO2 sensors, certainly in these in the times at the moment, to be able to get a heuristic for how well their ventilation systems might be working. But going forwards, I really believe that this is an opportunity for us to be having a bit more of a balanced and holistic approach to how we can manage indoor environmental quality. And we mustn't forget that energy efficiency is going to be critically important for us meeting our net zero ambitions. We've got to think about air quality as well as just ventilation, because bringing in more outdoor air might actually be exacerbating children's health over the long run. But we do need to emphasize this as low as reasonably achievable strategy for managing COVID-19 in buildings. Now, thank you for listening, and I'm looking forward to your questions.
Thank you very much, Doug. That was really fascinating and lots of interesting data. And we have a number of questions in the chat. So there are two questions about air change rates. One in particular saying, you know, how did you measure them from Running Yao, and were they for mechanical or naturally ventilated buildings? And another question of, was that done independently of the CO2 measurements?
No, so to measure air change rates, we use the CO2 concentration decay method. These were, we're basing these on the end of school day exponential decay. We did have some exclusion criteria, namely around I think it was a 0.85 R squared. Anything that didn't fit that we didn't include in our air change calculations, but CO2 concentration decay.
So in the naturally ventilated case, I presume that you had to assume that whatever was open during the day was open at the end of the school day.
Yeah, likewise, you know, that's one of the challenges we had, where we didn't have this visibility in the classroom around when windows were open or not. So it's a very good point, and it's certainly a limitation of the data we have. We were making the assumption that, of course, that things were well mixed, when we know that, you know, the modelers in here aren't. That's not always the case, and that classrooms were being used in a similar way throughout the day.
Right. Okay, and a question now from Pete Knapp saying, are your mean CO2 values over the 24-hour period or the 8-hour working day?
So they were over the 8-hour working day, and it's a really important point, because otherwise, obviously, our mean CO2 concentrations would be much lower than they were for when the building was occupied. Yeah,
and while we're on CO2, which seems to be a popular set of questions, Paul Edgerboy is asking, since air changes per hour might not reflect the ventilation performance, how did you determine where to place your CO2 monitor?
Yeah, very good question. So the monitor, it was everything we're measuring, and our criteria where we tried to put it in the breathing height of the school children, away from corners of the room and not too close to doors or windows. But this is a really interesting point, because this is the sort of information which is needed and standardized so that when we are doing measurements in buildings, they're as similar as possible. I know that this sort of work is being done at the moment through PAS 3003, which might become a British standard, where they are trying to standardize these sort of approaches. So when we talk about classrooms, we're, not measuring apples and oranges.
Yeah, exactly. Thank you. I thought it was very interesting, your calculation of the risk of infection showing diminishing returns as you increase the ventilation rate beyond a certain amount. And Kate de Selincourt asks, with that, you did it in terms of meters cubed per second or something, I think. What about in liters per second per person, or something per second per person?
Well, there's not a number answer to that question. It's obviously going to depend on the geometry of the room, how many people are present in the room, and what we deem as acceptable, which is probably the elephant in the room, and is a question which we can't answer solely with data. It's something which we have to think of what our values are. What is an acceptable amount of ventilation to minimize potential COVID transmission against other mitigating factors, such as other indoor air pollutants, outdoor air pollution coming in, or indeed energy efficiency.
Yep. But I just wondered, you did show a number in terms of volume flow rate, and I just wondered if you were to recast that in terms of per amount of air per person, did you do that calculation, or is that something that
that's probably a calculation we need to do? I'd need to look through our data there and analyses to see if we have those figures.
Okay.
But I'll try and get in touch with you on that, Kate.
Yeah, thank you. Okay, and from Pete Knapp again, what advice would you give to schools who need higher ventilation rates but live near a busy road or other high pollution source? Likewise, what recommendations would you give to schools in the winter months for higher ventilation rates?
Yeah, these are the million-dollar questions, aren't they? So it depends on, number one, the ventilation type that are in these schools, whether it's mechanically ventilated or natural ventilation. We've done some work with superheads in the southeast, and even across 3 schools, the way the buildings operate is very different. Some have windows that can open, some don't. So I'm always wary of giving an overriding, a universal answer. What advice would I give, but live near a busy road? If the concern is much more around increasing ventilation rates, perhaps open the window facing away from the busy road, if it is at all possible. Perhaps open the windows during non-rush hour periods. Likewise, around winter months for higher ventilation rates, if you do have something which is based around natural ventilation, it's tricky. It's a case of you can't have it all by opening a window, perhaps, and focus on heating bodies rather than spaces. So encourage people to come in with more clothing. But what I really would hope is that during the period of time we have now between the spring and the winter to come, that we can start making some of the retrofit so that we can have more data-led solutions and technology-led solutions to answer some of these questions more comprehensively.
Right. And Katharina asks, I guess she missed your introduction, whether the black box behind you is the device, which it is. Is it? Can you move it and show us close up a little more about it?
Yeah, absolutely. I mean, anything. So we always consider this portable, but quite frankly, anything that you put on wheels is portable. So this is about 30 centimeters high, designed to look like a speaker, and to measure as many things as possible. We're doing some work on some new PhD projects which are designed at miniaturizing this technology. At the moment, this isn't appropriate for continuous monitoring. Quite frankly, anything that measures ultrafines isn't. It's too expensive. So we'll be looking at developing wall-mounted monitors that can do everything this can do apart from ultrafines, but certainly portable. It's we call our Rolls-Royce product. Creeping featureism.
Okay, and from, I don't know the first name, C. Sutton. In the US, the type of vacuum cleaners are taken into account in relation to particulates in the air. HEPA is recommended, for example, by the CDC. This isn't taken into account in the UK. The Royal Commission of Pediatric and Children's Health Working Party found evidence that certain vacuums resuspended particles in the air. Did you look at this at all?
No, we didn't. The averages we were looking at were during the working day for kids, but I think the point here is also very valid to school cleaners who come in. So we haven't actually looked at that data for that period where they might be cleaning and either resuspending larger particulates and or creating secondary organic aerosols through some of the chemicals that are used reacting with species in the air. It's an interesting point, and we'd have to have a look at our data again.
Yeah, I was also struck in the same way, your comments about extra cleaning associated with COVID, perhaps putting more undesirable VOCs into the atmosphere. And I guess there must be some sort of trade-off there too, presumably, in terms of general health and well-being of everybody.
Yeah, absolutely. We were to be involved with a project looking at the over-sanitization of residential areas with cleaning products, which was cancelled due to COVID. As you can imagine, the appetite for saying that we over-sanitize our spaces quickly disappeared. But I think that conversation is returning now that you see some of these air fogging technologies that are being used, and it's the unintended consequences. It's not even an unknown. We know that these are going to be bad for general indoor air quality.
Yeah. Okay. I don't see any more questions in the chat at the moment. I have one myself, and you've been talking about annual mean concentrations of various things and so forth. Do you think there's a case to be made, I don't know whether in the school context or generally whether the the regulations ought to reflect something other than those kind of very long-term mean concentrations and so forth? I mean, presumably, exposure over short timescales to very high values can be deleterious. And do you think there's a case to be made for changing the way we regulate air quality criteria?
It's a good question. I assume the toxicologists and epidemiologists, if there are any involved, will have a strong opinion on this. I'd say yes, but it really, it's a bit of a chicken and egg whether we have the evidence that shorter term exposures do have the sort of negative concentrations that we might think they do. There is some evidence of that for certain pollutants. But I think it comes again down to, it's a values question on whether we take a precautionary approach or whether we're waiting to see evidence of harm before we do act. So, I do find it interesting, and I can understand why, but air pollution can be illegal, and we can be sued for the European Union when it was outdoors, but when it penetrates into a public or private building, it's not the responsibility of government. Of course, it's complicated because the activities we do in buildings generate significant amounts of indoor air pollutants, but it sort of shows that we have to create these artificial divides between where air should be regulated and where it shouldn't be and what we should regulate. So it's a conversation where we need to keep having it, because we'll never get to a point where the regulation is good enough. It's just about, it's a continuous process.
Yeah, I think that's right. I mean, it's also the case that it's hard to regulate what people do in their own homes. I mean, schools may be different, but it's hard to tell people what they can and can't do in their own privacy of their own home.
On that case, we've done a lot of work in the residential environments where you can imagine cooking is a horrendous source of particulates, and if you have a gas stove, nitrogen dioxide. Right. But do we want to encourage people to stop cooking nice home meals and get takeaways? I enjoy takeaway once a week, but I'm not a public health professional, but it's probably not advisable to have it every day. So it's, it's a complicated question. It
is, absolutely. A couple more questions here now from Kate de Selincourt again. She asks whether the PM 2.5s and NO2, which you said was outside, was local to the school.
It was from the closest AURN station. In some of the schools, that was on the school property. In some, it was up to 15 kilometers away. So our judgments between inside and outside are going to be better in some cases than in others. Of course, I'm sure there are some wonderful modelers who attend these sort of events who could do a bit more with the outside data to extrapolate down to a closer spatial resolution. But you know, in some cases it was on the site and some a long way away.
Yeah, yeah. And from Graham Riot, how important is it to get the children involved, and to what extent?
Well, I think that's one of the great things about this network, that there are, and there was a presentation, I believe, last week on getting kids involved. From our point of view, in putting technology in, it's a better way for them to, I think, to enact the sort of change we want to see over longer periods of time, and not make the project purely extractive, where we're just using the schools as a means to run our experiment. It's about making the air visible to the kids so they can go and talk to their parents. You know, operationally, it's good to get them involved as well, because otherwise they turn monitors off because they don't know what it is and they want to see what happens.
Yeah. Yeah. And another question from Paul Ajiboy. We've seen sensors deployed in schools designed to respond to CO2 levels in classrooms. How do we ensure that these sensors are checked for performance drift in years 2, 3, and further on, etc.?
Right. So we always recommend the use of non-dispersive infrared NDIR sensors, because they're much better than this at these sort of questions and challenges. Long-term drift, more than CO2, it's a problem for some of the other sensors, the lower cost sensors. CO2, a lot of them have automatic baseline calibrations, which take a period of the day under non-occupancy to recalibrate on a daily basis. There is some pretty extensive work done looking at long-term drift problems. I don't know around years 2 or 3. Some of these off-the-shelf low-cost CO2 sensors you can get. CO2 is pretty easy to calibrate if you're after a indicative value, because you can take it outside on a Saturday morning and say 420 ppm, 0 here, which is much more difficult to do with other pollutants. So this is the sort of thing where guidance can be given to the teachers or the building operators at schools, where they can do these sort of things, which means the sensors will last for quite a long time.
Right. Okay, well, I think it's time to draw the questions to a close, and just to say thank you very much again, Doug. I think one of the things you said, which was very at the heart of TAPAS, is really about the indoor-outdoor exchange, particularly around the question of PM 2.5. And I was fascinated to see how you could see outside effects reflected inside in PM 2.5 concentrations. And these are the kind of things I think that we're, you know, one of the kinds of questions that we're very interested in this particular network. So thank you very much for a very interesting talk. And just to say to everyone that this is the last in this current series of seminars. We will resume again after the Easter break in the summer term, with further seminars. And we have a full network meeting taking place on April the 23rd. And Sophie has put the Eventbrite invitation in the chat. So we'd like to encourage you to come along to that. We have Kath Noakes giving a sort of keynote talk, and we're focusing to some extent on giving, well, we'll be giving both a summary of what we've been doing in the network up until that time, after about 6 months, and also talking to some extent about what's the impact of the pandemic on our thinking, because the project was established and proposed and established before the pandemic began. So and we've obviously all been influenced by it now, both in our day-to-day activities and the way we think about these things. So I hope you'll find that an interesting day, and we look forward to seeing you then and at our series after the Easter break. So again, thanks very much, Doug, for this presentation, and to all of you for coming. And Sophie's going to put up contacts. So if anybody wants to contact us, please either contact Sophie on her email address there, and look at us on our website and Twitter page. Okay, thank you all very much, and enjoy the rest of the day.